Welcome everyone to today's Explainer. We're diving into a really fascinating new framework for AI development, known as the energetic paradigm. You know, as artificial intelligence systems just keep growing at these completely unprecedented rates, a lot of researchers, investors, and tech leaders are starting to ask a pretty vital question. Is sheer brute force scale the only path forward? Or is there a more elegant, efficient way to build intelligence? So today, we're going to explore a conceptual framework that suggests accuracy alone might not actually give us the full picture of an AI system's true quality. Here is our roadmap for today. We'll be moving through the deep learning shift, the scale-driven regime, the energetic paradigm itself, redefining AI objectives, beyond post-training pruning, and finally, a resource-conscious future. Let's just jump right in. Starting off with Section 1, the deep learning shift. To really understand our current moment in AI, we kind of have to look back at the massive methodological shifts over the last few decades. Think back to the 80s and 90s. We relied heavily on classic rule systems, right? These were manually hand-coded features and explicit symbolic pipelines. But while they really struggled with the messy ambiguity of the real world, then came the 2010s and the deep learning turn, where models actually started learning internal representations directly from the data. And that leads us right into the 2020s, where we find ourselves firmly planted in the scale-driven era. There's a great quote from the source material that sums this up perfectly. The deep learning turn moved much of the burden of abstraction inside the model. While those classic systems stumbled when dealing with high-dimensional spaces, deep learning basically succeeded by making the neural network architecture itself responsible for feature extraction. We literally stopped telling the computer exactly what to look for, and instead we built systems capable of figuring it out themselves. A real game changer. Which brings us to Section 2, the scale-driven regime. Now, that massive success with learned abstraction inadvertently created a new structural bias. We call it the scale-first assumption, because larger models just repeatedly achieved lower error rates on all the benchmarks. Expanding the parameter count, dumping in more data, and jacking up the compute budget just became our default answers. Optimization became almost entirely about reducing predictive error. But here's the catch. This scale-driven regime inextricably links progress directly to rising energy costs, higher inference latency, and incredibly difficult deployment scenarios. The hidden costs of this intelligence are really starting to pile up on us. So the crucial point here isn't that scale fails. Scale obviously works, and it has produced some absolutely incredible scientific gains. The real problem is that our current objective functions don't penalize an AI for using an unnecessarily massive, wasteful structure just to get the right answer. If a model uses a highly redundant, hugely energy-intensive internal route to solve a problem, our current training methods simply don't care. As long as the final answer is correct, it gets a pass. Let's look at a proposed solution in Section 3, the energetic paradigm. Enter the energetic paradigm, or EP for short. It's essentially a safety-conscious conceptual reformulation of the training objective. It argues that we need to consider predictive error jointly with three other things: energy cost, structural redundancy, and representational coherence. And to be totally clear, the energetic paradigm is not a replacement for deep learning, not at all. Rather, it's a maturation of it. It's a complementary perspective that introduces a much-needed resource-conscious constraint into how these models actually learn. So we're talking about a distinct philosophical shift here. The scale-driven era basically assumes that more scale inevitably equals more capability. But the energetic paradigm proposes something different, that better internal organization yields more sustainable intelligence. It's a shift away from pure, unconstrained expansion, moving toward thoughtful optimization and transparent design. Moving on to Section 4, Redefining AI Objectives. So how exactly does this framework propose we change the way AI learns under the hood? Well, it essentially expands the rubric by which the AI is graded across four pillars. First, predictive error. Accuracy still fundamentally matters, of course, but then it adds three new metrics. Energy cost, which acts as a proxy for how much active representation or hardware is being used. Structural redundancy, which actively tries to minimize unnecessary computational paths. And finally, representational coherence, which ensures that as the model becomes more compact, it maintains a useful, non-destructive internal logic. Without getting bogged down in the underlying math, the EPOJ objective simply broadens the definition of what makes a successful model. Now, this raises a highly practical question, especially for the engineers and researchers listening. If multiple AI models achieve the exact same low error rate, like if they all get an A+ on the final exam, how do we choose the best one? Under a purely scale-first regime, we might just shrug. But EP actually gives us a way to decide. This brings us to a really cool concept, the near equivalent solution set. In complex AI, there are many different structural paths a network can take to achieve that low error rate. Some of them are super elegant and efficient, while others are incredibly wasteful and redundant. EP treats neural training as a constrained optimization over the set of equivalent solutions. It deliberately pushes the model toward the most compact, high information, and coherent configuration out of all the possible winners. All right, Section 5, Beyond Post-Training Pruning. For the tech leaders watching, you might be wondering how this differs from existing techniques. Specifically, why not just prune the model after training? It's a super common practice in the industry right now to train a massive, over-parameterized model, let it finish learning, and then just chop off the parts that aren't being used. But the energetic paradigm takes a fundamentally different and arguably much more profound approach. Let's quickly look at the standard post-hoc pruning process. Step 1, you select a model based entirely on its predictive loss, meaning its accuracy. Step 2, you apply a simplification step to remove wasteful components. Conceptually, pruning is basically asking whether a massive, wasteful solution can be repaired and simplified after the fact. It's quite literally an afterthought. The fundamental difference here all comes down to timing. Post-hoc pruning attempts to simplify a wasteful model after it has already been selected based solely on accuracy. The energetic paradigm, on the other hand, bakes these energetic preferences directly into the training phase itself. It asks whether the selection criterion should prefer models that are already less wasteful and more coherent during the learning process. It ensures the model is resource conscious from the very first epoch of its development. Which brings us to our final section, a resource-conscious future. To validate this entire framework, the research outlines a series of deliberately modest conceptual predictions. Rather than chasing massive, headline-grabbing performance leaps, these predictions test whether models trained under EP demonstrate fundamentally different, more efficient resource utilization compared to standard models, all while maintaining the exact same accuracy. The whole goal is to prove that structural efficiency is mathematically measurable and practically attainable during the training process itself. I love this quote from the source. The objective is framed as a way to reduce waste, clarify trade-offs, and encourage auditable efficiency rather than to accelerate unrestricted capability growth. For investors and technology leaders, this is absolutely crucial. It represents a reassuringly conservative safety posture. It's all about building transparent, manageable, and auditable systems, rather than just endlessly pushing the gas pedal on unrestricted scale. Of course, as with any academic framework, we have to thoughtfully acknowledge the limitations. The energy proxies proposed in EP are exactly that, just proxies. They don't perfectly capture real-world hardware costs, like memory movement or specific compiler behaviors. Furthermore, coherence metrics require incredibly careful, task-relevant design. You can't just slap a generic formula on it. And finally, if a model is underfitting, meaning it simply isn't complex enough to learn the task in the first place, pure scale might still be the genuinely necessary lever to pull. Ultimately, the energetic paradigm provides us with a profound conceptual framework to stop relying solely on brute force expansion. It suggests that the future of AI isn't just going to be about building larger and larger systems. It's going to depend heavily on deeply understanding how intelligence can be organized more efficiently, sustainably, and coherently. So, as AI development continues at this absolute breakneck pace, how are we going to measure our ultimate progress? Will it be by the sheer, staggering size of our models, or by the elegant efficiency of their architecture? I'll leave you with that thought to ponder. Thank you so much for joining me for this explainer on the future of efficient AI. I hope it sparks some curiosity, and I'll see you next time.